9.1 Lesson 4 Sequences. Our objective for today is you'll be able to use the squeeze theorem for sequences to determine the convergence of a sequence. So, vocabulary, squeeze theorem for sequences. We begin by reviewing the definition of the limit of a sequence. So the limit of a sequence is L, written this way, and here we have the epsilon m definition. But what I want to emphasize for today's lesson is the limit L of a sequence, if it exists, then we say the sequence converges to that limit. If the limit of the sequence does not exist, we say the sequence diverges. So look at the squeeze theorem for sequences. So this is similar to the squeeze theorem for limits that you learned in Calculus AB. But here we're applying the same concept to sequences. So look at this part here. So we have three sequences. The terms of one sequence are between the terms of two other sequences for all n greater than n. If that's the case, and you're able to show that the limit of the sequence whose terms are a sub n, if the limit of that sequence is L, and the limit of the sequence whose terms are b sub n, if the limit of that sequence is also L, then the sequence whose terms are between a sub n and b sub n for all n greater than n, the limit of that sequence must also be L, and thus showing that the sequence whose terms are in the middle must also converge by definition, because its limit would exist, because the limit of its nth term as n approaches infinity would exist. So if we wanted to show that this particular sequence here converges by using the squeeze theorem for sequences, what do we have to show? Well, we have to show that the nth term of this sequence can be bounded by the nth terms of two other sequences for all n greater than some integer n. And the other thing that we have to show is that the limit of the nth term of these two sequences as n approaches infinity is L. So by the squeeze theorem for sequences, we may then conclude that the limit of the nth term of the sequence under consideration as n approaches infinity must also be L, and therefore, by definition, this sequence must converge. And again, that goes back, of course, to the definition of the limit of a sequence. If the limit of the nth term as n approaches infinity exists, then we say the sequence converges to that limit. So when you take a look at the work here, we're showing two things. One, that the nth term of the sequence under consideration is between the nth terms of two other sequences for all n greater than n. And two, we're showing that the limit of the nth term of the two sequences, a sub n and b sub n, as n approaches infinity, is one and the same. So how do we show the first condition? And we want to choose these two sequences so that we can find the limit as n approaches infinity for the nth term of each sequence. So the sequence that we have here is the nth term is cosine of n divided by n. So we know that the output values of the cosine function are between -1 and +1. Could be -1, could be +1, but between -1 and +1 for all n greater than or equal to 1, where n is an integer. Here, for all n greater than or equal to 1, we'll divide each part of this compound inequality by n, and because n is a positive number, we don't change the direction of the inequality symbol. So this shows us that the condition here is satisfied for all n greater than or equal to 1, so that the nth term of the sequence under consideration is shown to be between the nth terms of these two sequences. One is -1 over n, and the other sequence would be 1 over n. So the nth term of the sequence under consideration is shown to be between the nth terms of these two sequences. So we've taken care of condition number 1. Now we have to show that condition number 2 of the squeeze theorem for sequences is satisfied. So now we look at the limit of the nth term of this sequence as n goes to infinity, and then we look at the limit of the nth term of the other sequence as n goes to infinity, and we want to see if they're the same. And of course they are, because the limit as n goes to infinity of each of these two sequences is both equal to 0. So by the squeeze theorem, we may conclude that the limit of the nth term of the sequence under consideration as n goes to infinity must also be the same value, 0. So by definition, our sequence, because the limit of the nth term as n approaches infinity exists, our sequence converges to that limit by definition. In this lesson, we were able to use the squeeze theorem for sequences to determine the convergence of a sequence.